Hello, everybody. Um, I want to thank everybody for showing up to our webinar dealing with the future of systems engineering. I appreciate giving me your time in order to do this. I want to thank uh, the um, the board of the Nkosi uh, uh, Central Arizona chapter for inviting me to do this presentation on the future of system engineering. This is something I did for the Washington chapter a few weeks ago, so I really appreciate them giving me the chance to do this. I want to thank Joe Marvin, Chris Gradusi, and Carl Lundrum as well. So thank you all for showing up. I want to just give you a few thoughts on actually how to work this seminar, because this is kind of new software for some of you, and I want to show you a few aspects of the software. As you can see, of course, you can see my face right there on the camera and voice. Um, the share on the side, there's a communication, there's a way that you can actually communicate with me. Down below, there should be a smiley face just below the attendees. And you can actually go in there and actually do several icons to show me that you can hear me. Like for instance, gotta remember I gotta go to the next one. For instance, you can raise your hand. That way, when we do, you have something in the chat, and I may be talking along and not see it. If you raise your hand, I'll kind of look down and be able to see it. And if you want to talk, I can definitely turn on your mic for that. The other thing you can do is if you disagree, I might ask a question of you and see how that works as well. And by the way, can you see the smiley face? There it is. All right, let me move this over so that it kind of shows up and make this a little bit smaller. Sorry about that, still trying to get used to this software. So if you see the little smiley face, go ahead and raise your hand just so that I know that you're listening. We're going to try to get a little bit of participation back and forth in here. Oh, good. I've got a few of you raising your hand. If you're listening on the phone, I don't believe you can do that, but at least you can hear the presentation. Also, what you're able to do is actually make comments. If you look down below the chat, you can actually write a message and hit send, and that way we can have kind of the communication back and forth. So it looks like some of you haven't found the little smiley face yet, but I'll give you a little bit of time to do that. One of the reasons I want to try to get you used to this software as we're working is I'm a little more comfortable with people in front of me, and this is the best way for us to kind of interact with each other. One of the reasons I can't, I can turn on your volume if you want, but the last time I had a meeting on this software platform where everybody had the vocal on, it just ruined the bandwidth. It was just too much. So it's much better just to have me talk and that way, and you do the electronic thing. So if that sounds like a good deal for you, if you could hit know that you guys are in agreement, that would be great. And as a matter of fact, let's go ahead and try the chat box right now. If you wouldn't mind going in there and just tell me where you're at, where you live, how many years you've been a system engineer, what Nkosi chapter you're with, because I believe we'll have more than just Arizona here, and what time it is at your place. The time we have right now is 8:32. So we appreciate you being here. A little bit about me. I've been working as a system engineer since the late 70s. Actually, it's kind of funny to think back how long it's been. But I worked as a product engineer for General Electric, a system engineer for NAVC. I've worked for NEMA, Army, DoD agency right now. So I've been all over the place, done many aspects of the system engineering process. That's one of the reasons I was able to get the ESEP. Also, I'm a UMBC adjunct professor where I teach system engineering to graduate students. I have an integration, implementation, and test class as well as advanced system engineering processes. And I've been teaching a CSEP exam prep course since 2009, pretty much using it to help students prepare for the exam, for the CEP exam. And I actually started an online business called SE Scholar this year just to kind of continue to push that scenario out. Also, in the past, I've been a board member for about 5 years at my local Chesapeake chapter. We have one of the better, I must say, because I was communications director. If you go to their website, I kind of helped build that from scratch in cozy-cc.org. We have one of the better, I think, chapters. Now, Arizona chapter, I'm sure you're pretty good too. That's about me. I appreciate you all putting in where you're from and stuff like that. It looks like I do have a bunch of Arizona and Texians, so that's great, and it's good to have you here as we go along. So let's get started as we go through this. So. Okay, so again, I appreciate you being here. This is a presentation on the future of system engineering. But first of all, I want to ask you how your day has gone so far. It's about 5:35 there in Arizona. And I was wondering, you probably jumped out of bed early in the morning, not realizing that the mattress, which, you know, having something soft to sleep on, I think, have been around since we've been in caves, but it hasn't been till the 1930s when you actually see the modern day mattress, the mattress that we associate with beds today, that they came along. And then you probably turned off an alarm clock. An alarm clock, well, clocks have been around since probably 700 years after Christ. It would be like in China, they had clocks. But the actual mechanical clock that would be, that you could set for an alarm, that was patented in the 1840s and all. So, but the modern day alarm clock, which used radio waves as well, a radio clock, that wasn't invented until after World War II. And then think about your clock and all your appliances, which you cook your breakfast with, is hooked into this alternating current that have been around since the 1890s. But during that time, there was actually this war of currents. There was like, will we go with DC or will we go with AC, alternate or direct current? Edison and his General Electric company really felt direct current was the way to go. But it was the Westinghouse that came in with their alternating current that won the day. So that's been around since the 1890s, and as you know, it took decades to get that system, the electric system, out into the world and people using it. And right now, it's probably the largest system on the planet. The way it's all interreacted with each other all the various electrical divisions and stuff as they're working and all. And then think about you turn off the alarm clock, you go into the bathroom, take a shower. Of course, the Romans had their public baths. They had kind of semi-shower type things, but all in the public. And it wasn't until the 1850s when plumbing was kind of reinvented and we were able to create the modern bathroom. But it was only for the rich. It took another 75 years for it to reduce in price for the common household. In the 1920s, people started putting bathrooms and showers into their houses and all. And then you look at after you take your shower, you dry off, you put on some clothes, not realizing clothes are it's absolutely amazing because clothes is one of those fundamental problems that had to be solved. How as a matter of fact, just to give you a story, I like listening to podcasts, and one of my favorite podcasts is Planet Money. And Planet Money did this 6-episode series where they actually talked about what it takes to actually create a modest t-shirt. And they talked about getting the cotton from the United States, taking the yarn, getting it done in Indonesia, and then from there it would go to Bangladesh in order to be sewed together, and then it would be thrown into these shipping containers, and it would be truck shipped, trained, and then trucked into a store. That whole process would be like $17. They would sell it for $25 and all. And by the way, the shipping, which you think, these huge ships and the shipping containers and all that's involved, that's pennies compared to all the rest of the aspects of getting the system out, getting the clothes to your store and eventually where you buy it and you put it on your back. And then you go make your breakfast. You're getting eggs. By the way, the egg carton has been around since 1910. I think that's an interesting fact. But think about what it took to get the eggs into your refrigerator. It came from a chicken, of course, huge amount, and they had to be washed, clean, put into some kind of refrigeration environment, and then shipped to a store where you could buy them. Just absolutely amazing aspects there. And then you get into your car. That's been around since the 1880s. In 1908, Ford came in with his assembly line, was able to pull that together. And by 2010, we have almost 1 billion vehicles on the planet for a planet of 7 billion people. So 1 out of 7, there's a vehicle for them. Absolutely amazing. And on top of that, you drive this thing on this complex aspect system of highways that have been around since the 1950s. And again, just an amazing system. And I haven't even talked about the cell phone, which has more power than it takes to the Apollo spacecraft. It has more power than the Apollo space program, if you think about it. And then the modern day office, all the aspects that have come into that to make our lives a little bit easier. And of course, the computer and the internet, just amazing man-made products. And basically what I'm trying to say is we live in this man-made world, and everything is complicated in terms of the way it takes for us to see these things. As a matter of fact, take something as simple as the pencil. As a matter of fact, there's this great author, Podolsky. He does these great books about engineering. And he did one just on the pencil. It's like 350 pages long, talking about this deep knowledge of engineering, technical history, examining the story of the pencil, considering it not just the thing in itself, but as exemplar of things that need to be designed and manufactured. And I guess my point is that everything needs to have this life cycle. It needs to be designed. It needs to be somehow manufactured. It has to be stored somewhere. Logistically, it has to get to the retailers. It's got to be delivered to them. It's got to be delivered to you as a customer. It needs to perhaps get broken and then repaired or just get rid of altogether. And all of that is a life cycle for every single thing that we pick up, buy, or get involved with. So there we are. We have our man-made world in the year 2014. But this is about the future of system engineering. And one of the things I was wondering about is, what does it take? You know, if you think about our man-made world, we're actually in yesterday's future is where we're at. And was there a way we could have predicted where we're at today? If you go 50 years back, as a matter of fact, Isaac Asimov did this great essay for the 1964 World's Fair, where he tried to predict what future 50 years from now would be. And actually, again, my Planet Money podcast, when I was just about to present this to the Washington chapter, it turns out when I was driving into work, lo and behold, it did a series on the 1964 World Series Fair, which was fascinating. Just talked about the way companies saw the future and things like that. So Isaac Asimov took that challenge. What would the future be like? And 50 years into the future, and it turns out he was pretty correct when it came to perhaps industrial robots or cable using light waves, optical cable, even Mars having robots on there, remote robots on Mars. He even thought through on widescreen TVs that would cover the wall, which we have. He did get it on that point, but he did kind of miss the lunar. He really felt we would have a lunar colony, which made sense back in 64 as we were trying to get to the moon. Wouldn't we just, the trend would be to eventually have a moon colony. And he really thought we'd have some kind of jet-powered car or underwater cities as well. So that didn't quite work as much as we thought we would do. So what's the bottom line? Hey, predicting the future is difficult, especially if it's prediction is very difficult, especially if it's about the future. A great physicist, Niels Bohr, said that. Although it could have been that philosopher Yogi Berra who said it as well. But the point is, it is very hard. But the question is predicting the future, it's hard, but it's also can be profitable, because you'll find yourself, there are plenty of companies out there who want to help you predict the future. They're looking at, companies really need this because they need to figure out what future revenues are going to be as they plan for industrial scenarios, trying to figure out where their domain and where their products would be going. And they need to plan strategically how to use those resources correctly as they're doing this. So you'll find that there are plenty of companies out there, be it Gartner or IDC or Cognizant, Industrial Research Company. All those will gladly take your money and then investigate the future for you and things like that. Fortunately, there's this magazine called Fast Company, and what it did was actually have an article that said, hey, these companies can predict the future, so can you, and they show you the various steps that's involved. Step one, you look at existing trends. Step two, you seek out these weak signals or trends to be. Step three, you extrapolate them into some kind of future. Step four, you assemble a scenario or some kind of concept of operations that deals with that, and then you backcast. In other words, look at what needs to be done in order to get to that future. and all. So what I want to find out is, can we do that when we look at Nkosi and what they did with this book, the 2025. By the way, great book. You can get it off the Nkosi website. When I'm done, I'll point you to our blog, and you'll be able to get all the links to everything I'm talking to you about here. So let's look at step 1 through 3, where you actually look at the trends, extrapolate them into some kind of vision of the future. And what Nkosi talks about is that trend where we're going to be leveraging technology to help our system engineering tools get even better as we do that. So we would see, for instance, cloud-based high-performance computing helping us with those tools that we need for modeling and things like that. Having advanced search algorithms to help us with some of our work for analysis and things like that, as well as some kind of virtual capability, being able to see these models in a virtual way. And then as well as being able to collaborate, because we're all putting our stuff on the cloud and we're able to pull it out as we think, as we start trying to work across the planet, coming up with these big, large systems. So that's kind of the trends they see. How would you extrapolate them into the future? And then they try to think up what would 2025 actually look like. And that's where they were thinking, this is where we would start understanding complex systems a lot better. We would have better collaboration because of those cloud computings. Our teams would be organized and integrated across all boundaries. Your system design would start thinking about the concept of systems. In other words, how do you apply your system in this greater system context? You start architecting the systems where you take the viewpoint of all the major stakeholders in order to get those requirements pulled together. And then you come up perhaps with the composable design that make more productivity. People can take these composite elements and put them together for a different type of system. Architect and design more resilient systems can take faults and be able to survive those type of things. Looking at cybersecurity in more depth as we go along. And then decision support using the information and analysis of perhaps big data as we're pulling that to end. And then virtual engineering, making that part of the digital revolution where we'll be able to see those models. So as you can see from this part here, we actually go into assembling the scenario and in order to show that it works. So that's step 4. What about step 5? How do we backcast to see what we need to take into account as we go forward? Well, one of the things the Vision 2025 has is this actually push to the path to the future. And what it does is it actually looks at establishing education and training roadmap. So basically what you look at there is you start introducing systems thinking early on in education, even as early as the K through 12. System engineering would become part of and you actually have some kind of theoretical foundation for system engineering as you go forth. In other words, system science would finally make a breakthrough and help us out. The other thing is establishing these research roadmaps where we start thinking about advanced system engineering methods and tools, all based on that theoretical foundation that we talked about before. The other thing, went the wrong way, sorry. Let me try this again. The other thing we want to do is establish the standards roadmap, and that's where we identify, develop, evolve standards in order to get the practice of system engineering and the system engineering body of knowledge more forthcoming out there. So that's the path forward. We also have some other things in there where we talk about standards and working with other engineering bodies to further system engineering. But the one thing I want to look at is this whole idea of establishing this grand vision, which would force the future by establishing this grand challenge. So I don't know if you can see it on the screen there, but it's that little upper left-hand triplet that talks about establishing the grand challenge. So what I want to think about is how does that force the future? So innovation through challenges is what I want to look at. And actually, if we go back to this idea of having problems with the longitude goes back as far as the 1500s. So as soon as we, as a civilization, started making ships, we found it was easy to figure out where we were latitude-wise. So we kind of can look at the sun, see where we're at, and it's fine. But looking at the longitude was totally difficult. There's just no way we do it. They would lose ships, entire fleets, because they could not figure out where they were on the planet. So back in 1500, Spain came out with a idea of a prize. They said, if you could solve this problem, we'll give you money. That nobody was able to figure it out by then. It got so bad that the British government came in 1714 and said, we'll give you 20,000 pounds. That's equivalent to like $2.5 million in today's money. And they said, if you can establish some kind of longitude solution as we're doing this. 1714, it took another 50 years before John Harrison, just a simple carpenter who was able to come up with a chronometer. It was a clock, and as you remember, clocks have been around since Chinatown, but to make them reliable and to survive a sea voyage was something that he came up with and was able to work through. So this was almost 200 years after Spain asked for a solution. But you can see this kind of challenge is something that can help solve those untenable problems that are out there. As a matter of fact, the Longitude Prize just came out in 2014 with a new prize where they're looking at ways to improve flight where it won't hurt the environment, or look at food where it's a little bit more sustainable. Antibiotics try to prevent the risk of resistant antibiotics, and also being able to help the paralyzed be able to move more freely, having safe, clean water for everybody, and of course helping people with dementia live independently a little longer. All very laudable challenges for the future. As a matter of fact, one of the best known and challenges out there is the X Prize. This is a nonprofit organization that actually designs and organizes these prizes in order to try to push solutions that will benefit mankind. One of the first ones was a suborbital space flight. I think they got like $10 million for it. And they were able to show that they could launch within 2 weeks of each other and get 3 people up into the suborbit. So that was pretty good. And then the one after that, like 2010, that was the 100 mile per gallon automobile. It's 100 mile per gallon equivalent, right? Because you wouldn't use gas. That was one of the key aspects to this. and they were able to give like I think 5 or 2 million for that. But they still have others that are out there: the lunar rover, the tricorder, ocean, having sensors and seeing how the health is for that. Again, all laudable things to push for the future through this grand challenge as we're doing that. So let's go back and look at the grand challenges that the system engineering that's in the handbook as we go on. And you'll see that it's actually kind of, after I showed you all those others, you read these, you're like, well, seems a little myopic. We're really into ourselves. It's true, we are. But there is a reason for this, and I'm going to kind of push this forward for you. One thing is just getting that core body of system engineering foundations all consistently taught in academia, so raising system engineers that have that foundation. System complexity would be embraced and understood and worked into systems. We'll be able to come up with resilient systems, come up with these model-based system engineering and much more better. Recognizing system engineering throughout the governments and industry and academia, that it is an innovative process to find solutions. Looking at technology assessments and policy analysis using system engineering principles. And then system thinking being taught at all levels of education from the very beginning of school to graduate school and beyond. So these seems like very in-house type grand challenges. These are something system engineers do need to do, but what is the reason for it? And actually I want to show you how, if you think about these grand challenges, how they can actually support the larger grand challenges of system engineering. Now, the National Academy of Engineering have their grand engineering challenges. They talk about making solar energy economical, getting fusion to work as an energy source, being able to look at your carbon footprint and the way that works, your nitrogen cycle, working all those in order to make our environment more cleaner and cleaner water, having an urban infrastructure that's improved, health informatics, better medicines, reverse engineer the brain, nuclear terror being prevented, better cybersecurity, better virtual reality, and advanced personalized training, as well as engineering the tools for scientific discovery. So think about all that I talked about from system engineering, getting those foundations in place in order to come up with the solutions here. Actually, let's go ahead and look at this right here, which is a video that's here to inspire us about the future. So let's listen to this.
Our society was built upon scientific and engineering advances. The engineering that helped drive things forward was, in large part, driven by people trying to make life better. In the field of computer graphics, we used reality as a benchmark until we started to make pictures that actually looked like they were real. Virtual reality is trying to do that in a real-time way so that you can interact with it in fairly significant ways. Then you can begin to convey new ideas to people. You can explore things which don't exist. So virtual reality is a way of making a larger space within which we can work and test our ideas and think and create. And the thing I love about engineering is trying to figure things out. How do things work? What do we do with them? How do we solve problems? This is creating the future.
The game industry has been around for a very, very long time. Some of the first programs it created were computer games. There's quite a number of people who are excited about the concept known as gamification. The notion is, can you use ideas from games to incentivize or motivate things in work? For example, brushing your teeth or filling out your taxes. What if, by doing these rather mundane work-like things, you get points, rewards, badges? In IBM, we're interested in trying to apply these concepts to education, training, compliance, security.
94% of life on this planet is in the oceans. We're just a tiny minority. We walk around on a little 1/3 and we call it Earth. 2/3 of the planet's unexplored. It's for the next generation. If we're ever going to understand this planet, if we're going to go in the oceans, we're going to have to move with these animals. We've got to go and fly in that space. When engineers dream, things happen.
What should we be doing now that will be needed 25 years from now? Well, why don't we develop the capability to network across the solar system in order to support manned and robotic space exploration? Why don't we figure out how to build a space-based internet? So we developed this suite of protocols, which we now plan to standardize for all the spacefaring nations. Then every time we launch a new mission to someplace in the solar system, we'll be able to use those protocols for the spacecraft to talk to each other and back to planet Earth. When they've completed their final mission, they can be repurposed to be nodes of an interplanetary backbone. So that's what engineers do. They turn science fiction into reality. That's engineering.
Well, that is exciting stuff as we're working this. It really is exciting to see perhaps the whole idea of gamification that coming to pass, as well as perhaps the exploration of the depths of the ocean, one of the great last frontiers in a space-based internet. Who would have thought? I mean, I guess eventually we will need something like that. So as we go along. But it really is an exciting time. The dreams that are out there, all of them are there in order to create solutions to help the betterment of mankind, trying to meet those human needs with system solutions that work together. I think that's my big point here, is that I say you're the system engineers that are the forefront of those innovation and invention that we need to bring into play in order to make sure that a better world will come into place, and then we'll have a brighter future as we're doing this. So I guess my point is you are the key to the future in order to make this work as well. Let me end with Alan Kay, who kind of came up with the object-oriented software, graphical user interface, just one of the great innovators for computer science. And he said, don't worry about what anyone else is going to do. The best way to predict the future is to invent it. And to go back to what the National Academy of Engineering said in their presentation, it said, applying the rules of reason, the findings of science, the aesthetics of art, and that spark of creative imagination. It's system engineers that'll continue that tradition of forging a better future. So that's the future of system engineering, the way I see it. I know we went kind of fast, and the slides weren't doing as well as I hoped they would be. But I'm going to go ahead and see if you have any questions at all as we're going along. It looks like you said, could you provide a title? Yes. And as a matter of fact, what I'll do for that YouTube clip is I'll put in the actual YouTube link to it as well. As a matter of fact, there are actually several other videos that are very exciting to see as well. So you may want to try them out as well as we're doing it. I'll be sure, yes, I'll bring all the resources for you, as well as the grand engineering challenges as well. Now, if they're, I think I want to go ahead and turn it over to Christopher. He would like to say a few things about the Arizona chapter. One of the things I want to encourage you to do, if you are part of the chapter, is get involved with chapter. One of the main reasons I was able to get my ESEP is because I had a good 5 years on the board, and they count that towards the leadership aspect of the ESEP. But it's also really good for your career to be able to network. And it looks like I lost everything. Is everybody still there?
Hello, Paul. Can you hear me?
Okay. Yes, there you are. You are working.
You can hear me, Paul?
Ah, okay, you should be. Let me try that again. Sorry. Chris, I think I inadvertently took you, turned you off.
That's okay. Can you
Go
hear
ahead
me?
and try again. Yes, I can hear you.
Hopefully
Okay,
everybody
can you hear me?
Yes, I can. I have
Okay.
been. So I
Okay.
wanted to thank you very much on behalf of the Central Arizona chapter for your presentation today. Very interesting topic. Thanks again for taking the time to put this together.
Yeah, and I wish we.
What I wanted. Go ahead.
Yeah, I wish we had a better means to go back and forth. I think the chat is the best way to do it for now. But maybe in the future, 10 years from now, we'll be able to have these full up, everybody have a video in there, but not quite yet.
And for those in attendance, I just wanted to point out two things with respect to the chapter. If you've received email communication from Carl Landrum, hopefully you've received the information and link to our chapter survey. We very much would appreciate if you could go take a look at that and provide your input. It helps us in our planning activities. And secondly, we do have open positions. If you are interested in any way of getting involved in the chapter, please back to Carl, and we can get you plugged in that way.
Great.
That's
All
all I
right,
had.
great. Okay, great, Chris. Thank you so much, and I echo that. Really, if you can find the time to get involved, it really is a great opportunity for your career to do that. I really appreciate. I'll stay on board for a while here if you have any questions or want to talk a while. But this will be about it. I hope I inspired you a little bit as we go forward with system engineering. It is a great profession, but we have a long way to go to make sure that we get the word out that it's a great way to go about coming up with solutions in the future. All right, so I'll hang on here, and the rest of you, if you have to go, just hit the end session, and you'll log out. It'll probably take you to my web page if you want to look around. There is a blog aspect on there if you want to see the resources right away. I have a blog entry for the Washington chapter, and I have the same resources there. All right.
Paul, I do see a question in the chat.
Oh my gosh, it's hugely long. See what it says. Jeffrey, probably should get you. Yeah, standards. 15, 29119, testing suggested significant opposition to the ISO standards, at least in the test community. What do you think is happening and what can be done to mitigate the resistance? It's actually interesting when it comes to system engineering standards, because it turns out that the in COSI for our handbook, the same person who's working that is working 15288. So we do have some synergy happening there. I'm not really sure if the ISO 29119, I'm not quite sure about the opposition, but the ISO 15288 is coming out with a new update. So I'd be interested in hearing from you, like once you read the 2014 version, and I believe that'll be coming out at the beginning or what's today, September, either October, November, in the next few months actually. 15288 will be coming out. So it'd be interesting to look at that and compare it to what 29.11.9 has to say. So yeah, sorry I couldn't be as helpful there. So all right, so I think that's it. If you want to hang on, I can turn your mic on and we can talk. But other than that, I think we're done for the evening. Thank you all for coming. You can go into the hand thing and hit agree or something to make me know that you agree that this was a good time. So, all right, we got a few pluses. Thanks, appreciate it. Thanks, guys. Really appreciate it.
Paul? Paul, can you hear me?